Greetings. In this one, we will talk about the method of sections in order to find the tension and compression forces in members of a truss in a more effective manner than if we were doing a method of joints, because we can choose which members to directly find the forces about instead of having to find all members' forces gradually going joint by joint in the method of joints. So this is another method for trusses, and it is precisely used to find the forces in members. And so the example that I'm considering is as follows. We have this truss made of three equilateral triangles, so all the sides of these three triangles that make up this are equal, and I set their length of sides to 1. So all the sides are equal to 1. That means that all the inner angles, so each side is 1, and all the inner angles are pi over 3, so 60 degrees. And also we'll name the points that create the sides, so ABC, BC, DE, naming them around like this. Of course, naming is up to you. And then we will also mention the external forces that are there. But I'll work with the external forces in an external diagram where I don't have a mention of the degrees and of the side length because we need a little more space perhaps. So I'm going to redraw the same thing once again. And now I'm just going to focus on the external forces to take care of global equilibrium first, which means that I have these trusses and our final goal will be to find some inner forces inside the individual members, inside the sides of the triangles in other words. But first of all, I have also some other external forces applied, some reaction forces for the supports that hold this whole structure in place, the truss as a whole. There will be AY, then there will be BY, here from above we could call it CY, but we have a number for it already. It will be 10 newtons like this, going down on the point C. You see the thing on the right is just redrawn, the same thing, just without some letters and numbers to make more space for the calculations that we're now going to carry out. And that's it basically. Also we have AX, but it will turn out that that will be 0 because we have no other horizontal force that in the equilibrium state of and in the static scenario for adding up all x forces, there will be nothing to repel it or to compensate for its magnitude in the opposite direction. Therefore, AX will end up being 0 in any case. All right. How can I find, for example, well, this is not B on the right side, by the way. That's going to be called dy, dy, not by, but dy. In any case, now I'm going to want to find dy and AY and AX, because those are not determined yet. So that's the first step. That's still not the method of section. This is just getting the outer forces. So I'm going to use the equation for moment around A. So sum of all moments around A should be equal to 0 by statics. And then I'm going to say counterclockwise is positive. So what forces cause what moments? We'll add it all up based on the distances. So remember, all these triangles have equal inner angles. All three inner angles are equal. All three sides are equal. And all sides are length of 1. So that's going to simplify our calculations a lot. So if I do the moment about A, first I'll take into account the 10 Newton force. To speed it up, I'm going to leave out the units, but hopefully it will be clear that we're talking either about the moments or the forces. I'll be leaving out the units, just working with numbers to make it easier to write it all out, as we don't have that much space on the screen. But in any case, imagine that the units must still be there. So first of all, the things that make a moment around A, there's a 10 newtons and it's going clockwise, which is going to be seen as minus. So it's minus 10 times. How far is it? Well, we have half of this triangle, and then plus the whole side here. So from a horizontally it's 1.5. So we've got that, and then add by is going to do anti-clockwise, therefore it's positive. That's actually going to be the result of the equation after we solve it. We were looking for by, and that is exactly 2 units far horizontally from A. Now I solve for this, and it will turn out that by is precisely 7.5. With units, it's 7.5 newtons. Right? I can write it here. Although might rather write it here. All right. So 7.5 dy. Again, this was a typo, so dy. So this dy is 7.5 newtons, and then ay, we do equilibrium in the y forces direction. So all has to be 0. What we have available is ay going up, that's plus, minus 10 going down, it's minus, and plus dy. So dy, and we know dy is 7.5 already anyway. So ay is 2.5. And it's going up. That was also guessed right. The arrows are guessed right when the result ends up being plus after the taking off moments, because if we reverse the force direction compared to how it should be, then the moment is counted with a minus sign, because we're always orienting the moment depending on what kind of rotation that force causes. And if we switch the direction of the force by 180 degrees, the sign will switch. So then, if we get the negative result, that's the reason why we switch the sign back, perhaps. Or we can switch the direction of the force and delete the minus sign. Alright, so we got the reaction forces. Now for all forces in x direction, we see they have nothing repelling the ax. So ax kind of can be ruled out of the equations. So I'll delete what we have, because, or perhaps the left side here will delete, and ax I'll also delete. Well, we'll have to redraw the points because those were lost now, so alright, so if something was lost now, so I'll redraw it. So it was like this: A, B, C, D, and E. Alright, and okay, this we should also delete. Now we'll do the method of sections, and okay, to make it even simpler, I'll actually write just the values without the names for the reaction forces, because that also takes up a lot of space. So this is 2.5 newtons going up there, and then by, that was 7.5. So we'll do that, going up, and then the 10 newtons going up there, that's not gonna take any more space, so we can leave it. Alright, so we have those three things, and now the point of method of sections is we should first know what we're looking for, and namely, I would say which forces in which members, which of the sides of this truss we're looking for. So let us look for these three. So what is the force in this member, and this member? So BC, BE, and AE. What are these three ones? Well, what I can do is, by method of sections, I can create a cut straight through here like this. What that does, is actually very useful because it lets us directly in this equation we'll be directly able to calculate the things. And we will not even need actually the support reaction at D, perhaps at the end of the day. And how it works is basically where I draw that line cutting through, I will create like a new free body where I cut through, those members will end, and I will just replace them by like arrows. So those members who were cut through the right side, I will choose the left side. Now I can choose either side, by the way, depending on where there's a quicker way towards getting the result done. But for this example, I'm gonna choose the left side. And what means choosing the left side means basically eliminating everything that is drawn on the right of the line of cutting that I drew here. So C, D, and E will no longer be in my new drawing. I will only keep the A and B there, and the members that were cut through will become arrows. So what I have left after the method of sections is basically this thing was cut through, the A was cut through, I'm replacing it as an arrow, and this as an arrow, and this, the BC, also as an arrow. I can actually write what they are. So BC, this is BE, BE, and this is AE. Alright, so this is going to be directly contributing to our calculation, because we will view these members as forces basically. So that's the point, that's the trick here. We can take a body and cut off the other part, and then or cut through it, and then choose one of the sides, and whatever members were cut through, we replace them by arrows. And we don't know the this direction of these arrows yet. They might switch, but I will guess them in intention going away from the chosen side. So they kind of go away from the rest of the arrows. They're all going outside. I could also guess them otherwise. And again, minus signs will mean I switch the direction. So that's the idea. I'm gonna also label the remaining endpoints. So A and B are still in the drawing. And now we can work with this. And I'm just gonna keep the AY. So AY is still there. We have to keep the reaction forces, the external things, external forces for what we are left with. So if I chose the left side, the only external one there is 2.5 newtons at A going up. So we have to keep that. So that's still applied at A. Still apply the A like this. Make sure it's visible. So 2.5 applied at A still. And now I can work directly with what we have, and we can actually solve for B, B, C, and A very fast. So what I have to do is now use, for example, the moment around some point and get some results. So for example, I want to look for AE. So I will take the moment and I can apply the static conditions of equilibrium like we did for the whole body before the cutting, for the whole thing, including CD and E. I will again apply the methods of static equilibrium only to this cutout, and it will work. So this AB with these three arrows, it will work for it also. So I'll take, and I can go in different order, I can choose different ways of doing it, but I will now, for example, take a moment about B. So it should equal to 0, again, the same condition apply. And I just have to determine the distances. So by trigonometry, AE is vertically square root of 3 over 2. Because of this angle, the angle at B, in the inside angle is 60, and then half of it is 30, and I create a height from AE to B, and that will be square root of 3 over 2. So my distance there is square root of 3 over 2, and the AE with this guess direction will cause a counterclockwise moment, a counterclockwise rotation, so it's counted as positive. So AE times square root of 3 over 2, and plus I have to add the remaining things. So I'm doing it around B, so the B things get eliminated, then A also. A will be half, well, we have to calculate the distance there again. So we see that A is horizontally 1/2 from B. And it's going to do clockwise, that is minus. So it's minus 2.5 times 1/2. All equaling to 0 as we had there. So we have that. Now I would perhaps, we can do different things, but I would write, we can say that the 2.5 is 5/2. Then 1 times 1/2 is 5/4. So it's going to be written the equation as this. We could also multiply both sides by 2, but I will multiply both sides by 2 over square root of 3. And that will yield, we'll just take this space, then delete the space that we will need for the next calculation. So A will end up equaling to 10/4 times square root of 3, which is 5/2 square root of 3. This. So we have that, and we got A directly. So actually it ended up being positive, so the guess direction to the right is right. So 5 square root of 3, and well, actually it's 5/2 square root of 3, so we'll just write it like this: 5/2 square root of 3, like that. Alright, so we have A, and now we need to get BC, for example. That's the only other in the x direction. And with the help of the equilibrium of x direction forces, I will directly get that to be something. So we calculate A, I can get rid of the calculations. And so if A to the right is 5/2 square root of 3, and then we have actually in this case not yet can we conclude that, because we will first have to also determine BE before it's not just BC being against it in x direction. For that reason, I would now take care of BE. So BE is the one that's diagonal going to the bottom right, and I will use its y coordinate and compare it to A, the AY 2.5. So that's gonna create again. This is, I'm not writing it, but this is the equilibrium equaling to 0 of y forces. So 0 equals 2.5 going up minus the y coordinate of BE, which is BE times, and now what is that going to be? It's only the cosine of, basically cosine of 30 degrees, which is square root of 3/2. And that is, well, this was minus, by the way. So minus BE times square root of 3/2. And now we can reorganize this equation. So BE equals 5/2, that's a 2.5. And I'm going to multiply both sides by 2 over square root of 3. So we get this, 5 over square root of 3 should be BE. And so we got BE directly from this equation. So the same, completely same thing, like taking the global equilibrium of the whole body. After the section method of sections, the section part will behave the same way. That's the main point. So this calculation we can get out of the way. And we can continue. So we've got an A and B, and now horizontally we only need BC, and we can get it very, very easily. But we see that everything that has a horizontal component so far is going to the right, and the only thing that can resist it that's left is BC, so it must go to the left eventually. we see both BE and AE only have horizontal components that go to the right, and A has no other components than Y. So BC has to will have to go against both BE and AE in X. So what I can say is that first of all, this expectation that the arrow will point in the right direction is wrong. BC has to go to the left now. So it goes like this here. And BC will have to be equal to the X components in magnitude of B and A. A is fully X, so AE is 5 over 2 square roots of 3. And then plus the X component of B. What is that going to be? It's going to be 5 over square roots of 3 times the X component is basically sine of that 30 degrees. And that is 1/2. So times 1/2. And that is in total 5 over 2 square roots of 3 plus 5, so it's actually 10 over 2 square roots of 3, which is 5 over square root of 3. So BC is the same like B actually. So we got that. So we got all these three solutions that we wanted. We got basically, and this might be confusing, it's just a calculation line. It doesn't is this in the original drawing, so it's not a member that we could analyze, but we were looking for this member, this and this, and we got all three. We got even their directions and their magnitudes through this method of sections.